Okay, so today, as I promised, finally we will start talking about lower bounds. And I actually already put the notes for today on the website, so you can take a look after lecture. I think it's section 3.1. And I will, I want to talk about general techniques for proving lower bounds. Of course, I will apply these techniques to specific problems so you can see them in action. Today, you're going to see the compression-based idea for proving lower bounds applied to both the distinct elements problem as well as to the quantiles problem. So two problems that we've already seen in class. So let's get started. There are a few different techniques. So for example, there's the compression-based arguments. And two, there's, let's say communication complexity. And these are not actually, they're not necessarily, I guess, disjoint techniques. I mean, in fact, some communication complexity arguments, the way you carry them out is via a compression-based argument. So there is some overlap between them. You don't know what these terms mean yet because I haven't told you, but these are two not necessarily disjoint techniques that are commonly used to prove lower bounds for sketching algorithms. Today, we're going to focus on specifically compression-based arguments. And this is my terminology. I don't know if you'll find, this categorization written anywhere in any textbook or in the literature. Communication complexity is a term that people standardly use. Saying that a lower bound is a compression-based lower bound, I'd say that's my terminology. What do I mean by that? What I mean is, we're gonna prove theorems of the following sort. Arguments of the form suppose there exists a sketching algorithm A for some problem like distinct elements or quantiles. Using S bits of memory. Then there exists an injection F mapping some set S, not S, let me not overload there. Mapping some set, let's say, call it Q, into, let's say, 0, 1 to the S. And it might not necessarily be 0, 1 to the S, it might be 0, 1 to some function of S, 0, 1 to the root S or whatever. But basically there's an injection mapping some set into some bounded set. So, right, 0, 1 to the S has size 2 to the S. So it's mapping Q into some bounded set. Therefore, you cannot have a bigger set, you cannot have an injection from a bigger set into a smaller set. So therefore, the set Q has size less than or equal to the size of the right-hand side, which is 2 to the S, right? Therefore, 2 to the S is at least the logarithm of Q, or in other words, S is at least, this should have been the size of Q. Or in other words, S is at least log base 2 the size of Q. Okay. Now there can be a lot of cleverness in how you actually carry this out. How do you actually prove that the existence of a good algorithm implies that there's this injection? How do you identify what Q should be? That's kind of the art of proving such things, and sometimes they can actually get quite complicated carrying this kind of thinking out. And you'll see today, our very first argument, compression-based argument for distinct elements, will be a very simple argument, and then the next arguments that prove stronger lower bounds will get a little more sophisticated, not too crazy. There are arguments out there that are even a little bit crazier. Okay, so let's proceed. So we're gonna apply this to both distinct elements as well as quantiles, as I said. So example, distinct elements. So remember what distinct elements is. You see a stream of indices, I1, I2, IM, which are each in the interval from 1 up to n. Okay. And if you remember, the algorithms that we talked about in class were both randomized and approximate, right? So in class, we showed that there are space-efficient algorithms that, randomized algorithms that output t tilde. T, let's say t is the actual number of distinct elements in the stream. T tilde is the algorithm's output, which is trying to approximate t. That output t tilde is such that the probability is over the internal randomness of the algorithm. The probability that t minus t tilde is bigger than epsilon t in magnitude is at most delta, right? So, there are some natural questions here. I'll say, one, is approximation necessary? And two, is randomness necessary? Okay. And, so for example, when I say is approximation necessary, what I mean is could we hope to have a randomized algorithm? Okay. Which with probability 2/3 outputs the number of distinct elements exactly. And with probability 1/3 might fail to do so. And when I say is randomness necessary, I mean, could we have a deterministic algorithm, which is always guaranteed to output the number of distinct elements to within, say, 10% error? And also we want this algorithm, of course, to use sublinear memory. We want it to use very small memory. And the answer to both of these questions is yes, they are necessary to both questions. And the proof of this is actually back to 1996, Alon, Matthias, and Segedi. Okay, so we will see the proof of this today, okay, and more. So let's just do a warm-up. And it's a good warm-up because we're going to use some of these ideas in the actual lower bounds, the more sophisticated lower bounds. Okay. And this warm-up is a compression argument. So theorem. Let's see. Suppose script A is a deterministic and exact algorithm for distinct elements using S bits of memory. Then S is at least n, right? I'm saying here that the elements in the stream come from a universe 1 up to n. So this is really saying there's absolutely nothing non-trivial. I mean, you can always just maintain a bit array of length n and solve distinct elements that way, right? So this theorem is saying there's nothing that's even minutely non-trivial in the space of deterministic exact algorithms for this problem. Okay, so let's prove this. And remember, I said we're going to show that the existence of such an algorithm implies an injection from some big set into some smaller set whose size depends on S. So we'll show that there exists an injection, which I'll call ENC, stands for encoding. So the injection is an encoding that maps elements of 0, 1 to the n into elements of 0, 1 to the s. And this, of course, if it's an injection, that implies that s is at least n. Okay. So, ENC is just a function. I don't really care that any of this is algorithmic, right? Because at the end of the day, I'm just trying to prove this lower bound, right, against the memory. It doesn't matter that the injection is efficiently computable or anything like that. Here it will be, but in general, that's not required to make the proof go through. So let me tell you how this encoding works. So suppose we're given some x, which is in 0, 1 to the n. We can interpret x as a set, what I'll call, let's say, capital X, which is the set of all i's such that xi is 1, right? That little xi is 1. So capital X is the set, little x is like the indicator vector of the set that just tells you which things are in the set by putting a 1 there. Okay, so what is our encoding going to do? So, how does the injection work? We'll artificially create a stream containing all I in X. Okay. Then we will run script A on the stream. Then the encoding of X is the memory contents of script A. Does that make sense?
What's the difference between small x and big X?
So we're defining an injection. I mean, I could have just defined, I guess I could have just defined the injection from the power set of 1 to n, but little x is an element of 0, 1 to the n, so it's a bit vector of length n. Capital X is a set. It's the set of all I such that little xi is 1, right? So if you have a 0, 1 vector, you can interpret it as a set, right? You can interpret it as a subset of 1 to n. Just where the ones are tells you what's in the set. 0 means it's not in the set. Does that make sense?
Okay.
Yeah. So, right, so just to make sure we're on the same page, let's say that little x is the vector, 1, 0, 0, 1. And of course, this is right here, this is coordinate 1, coordinate 2, coordinate 3, coordinate 4. Then this leads to capital X being the set 1, 4, which leads to the stream being 1 and then 4. Okay, and then we're going to run script A on this stream. Okay, and kind of what is like an algorithm? You can think of an algorithm as, or what is it? How do I describe the run of an algorithm? Or the state of an algorithm. I mean, an algorithm basically just has some controls, which is like the code used to define the algorithm, and then also its memory state, right? And its memory state, I told you, is an S-bit string. It uses S bits of memory. So, this algorithm, it's running on the stream, it's maintaining some memory, which is S bits. Now we're done with the stream. I can just take the memory contents, and that's an S-bit string. So that is my encoding. That's what I map X to. Okay. And what does the decoder do? Right. So, okay. So, I need to convince you that this function is actually an injection, right? Just to make sure that we all are on the same page here. Injection just means x not equal to y implies, right, f of x is not equal to f of y. It maps different things to different things in the domain to different things in the range. So I need to convince you that if x and x prime are two different strings, then their encodings will not be the same. The memory contents of the algorithm have to be different for different strings. Right? That's what we need to show.
I mean, isn't that just by definition of having an exact algorithm, though?
Well, no. Okay, well, I mean, it's not going to be that complicated, but you do have to argue something, right? Because when you query the algorithm does not give you x. The algorithm gives you the number of distinct elements, right? So, like, for example, let's say here I gave you the string, I gave you the vector 1, 0, 0, 1. What's the number of distinct elements after you run A on it? It's 2, right? In this example.
But I guess, like, if I have two different streams that had the same memory contents, then
Right.
the algorithm cannot be outputting different answers, even though the distinct elements are different, right?
Wait, sorry, say it again.
So like if I run my algorithm on,
Let's say we
like
ran
two
it on
different,
this thing instead, 1100. If you
right,
query the
like
algorithm for both of these, it's going to say 2, right?
I see. Yeah, okay.
But that's not clear. It's not clear a priori. I mean, there is a simple argument. You'll see it in a second. It's not clear why these two vectors, need to have different memory footprints for the algorithm, because the algorithm can say 2 for both of them, right? So as long as the memory is telling the algorithm say 2, what's, why can't that be true? And the answer is definitely a number between 0 and n, right? Because we're only talking about n length vectors here. So this basically the number of distinct elements is the support size of the vector, or like the number of ones in it, right? Which is a number between 0 and n. I can represent a number between 0 and n using basically log n bits. So why can't I get away with an algorithm that only uses log n bits? It just needs to remember the answer, right? And so that's what I'm going to show you now. I'm going to show you that, in fact, the algorithm needs to use n bits. And the way I'll do it is I'll show you basically an inverse. I'll show you that you can invert the encoding and get back x exactly. Okay. So since it's invertible, it must have been an injection. So here's the inversion function, which I'll just call the decoding. So the decoding takes as input, let's say m, where here m is like the memory contents. So it's an s-bit string. So the first thing I'll do is I will initialize the algorithm with that as its memory. Okay. And then what I'll do is I'll ask, what are the number of distinct elements? So I'll say s is equal to a.query. And then I'll initialize my return value x to be, for now, it's going to be the all zeros vector, but I'll gradually add some ones into it as I discover ones. And then I'm going to have a for loop for I equals 1 to n. I want to determine, is xi 1 or not? So what I'll do is I will append I to the stream. So a.update I, right? And then what will I do? Then I'll query a. Okay. Remember, this is an exact deterministic algorithm. So tell me right now, what are the possibilities for R? There are only two numbers R could be right now.
It could stay the same, or it could have increased by 1.
Yeah, exactly. It either stayed the same or it went up by 1. Now, when do those happen? Basically, if this is the first time I'm seeing I in the stream, it'll go up by 1, right? But if it's the first time I'm seeing I, that means xi had to have been 0. Otherwise, it would have been inserted in the stream by the encoder. So basically, xi is 1 if and only if R did not go up. Okay, so if R didn't change, so if R is still equal to S, that means it must be the case that xi was 1. Then I'll set xi to be 1. And then now I'll update S to be what R is. And then down here, I return X. Okay, so that's it. So this is indeed, it's something that's not too complicated. And I'm just showing you here that, in fact, the encoding is invertible, right? Let me not be pedantic. I mean, I hope everyone is understands. Let me know if you have a question, why this thing works, right? It's just item by item or index by index trying to figure out whether or not that index already appeared in the stream of the encoder. And it's able to do so exactly. Yeah, so there was a question from Edward. If we have that m is much less than n, then can't we just store the numbers we see using m times log n bits? And that's true. So, but if you notice in this proof, what is the length of the stream m? The length of the stream m in this is at least n, and it's at most 2n, right? So so I guess I should qualify Suppose A is the deterministic exact algorithm for distinct elements using S bits of memory, on streams, let's say on streams of length, omega n, right? Because in our lower bound, indeed, as you point out, Edward, you need the length of the stream to be linear if you want a linear lower bound. Okay. Any other questions? Okay.
Sorry, Joel.
Yes?
Just real
Yeah.
quick. So
Yeah.
you if r is equal to s, you set xi to 1, but that's because you know that in the original xi it's equal to 1, right? I'm just confused.
Yeah.
It says,
Right. X is the thing. So right, the decoder doesn't know x. The decoder is trying to figure out what x is.
Right.
So initially, he just sets all the entries of x to 0, and then one by one he tries to figure out whether that index was actually a 1. And yeah. So is that? I don't know if I'm just kind of.
So I just mean the xi. So there's you say if r is equal to s, it says xi is equal to 1, and that means like in the original case.
Oh yeah. That's right.
Sorry, that's all I meant.
And for the vector that was encoded, not for the x at the earlier in the pseudocode.
Okay, thank you. That makes sense.
Or maybe this will make it clearer. Okay.
Yeah, that works.
Okay. Any other questions?
Yeah, actually I have two. So the first one is, can you go back to the previous slide?
Yep. Okay.
So basically the issue in this example that you drew was like, if the algorithm had the same memory contents after 1.4 and 1.2, then if I take those two outputs and then I queried again, or if I input again if I again input 4, then at least one of those would have stayed the same, and then there would have been an error, right?
There would not be an error. You mean it wouldn't give the correct number of distinct elements? Is that what you mean?
Yeah, exactly.
Right. So I guess the point is, let's say for those two different streams, in one of them, if you inserted 4, or let's say if you inserted 2, then the number of distinct elements wouldn't go up, and for the other it would. That's right.
Yeah. And then my other question was, what you had said before about the length of the stream, is it the length of the stream that matters, or the possible integers? Like we have integers 1 through n. It seems like what
both,
matters,
right? I mean both, because there is an algorithm that uses memory big O of the min of m log n and n, right? Like both.
Sorry, what is little m here?
M is the length of the stream.
Oh, okay, yeah.
Right. So, this lower bound needs to make an assumption about m. Otherwise, you're not going to get an omega n lower bound.
Got
otherwise. I mean, really, what you can say is actually this lower bound here is actually proving a lower bound of omega, the min of m and n. Right. You can view it that way as well, because you can say, look, suppose that I tell you that I want a lower bound for streams of length m over a universe of size n. Okay. Well, if m is much less than n, then what I can do is I can just run this argument and not use the last part of the universe. You know what I mean? I can just encode strings of length m.
Yeah.
And I would still get I would get an omega m lower bound. Okay. Any other questions? Okay, so let's move on to something a little more sophisticated. What about deterministic and approximate algorithms? Is that possible? Can I have a 10% approximate? It's guaranteed to always give me a 10% approximation with probability 1. It's a deterministic algorithm. Is that possible? And it turns out that's not, unless again you use omega n bits of memory. And I want to prove that. But before I can prove that, I'm going to need to take a little bit of a detour and talk about error correcting codes. Okay. So definition, what is an error correcting code? Okay. A code is just, let's say, a subset of, let's say, call it Q to the L. When I say, by the way, when I say like bracket A, what I mean is the set 1 up to A. And just some terminology here. Q,
Bless you.
thank you, is what's called the alphabet size. Just give me 1 second. L is what's called the block length. This is just jargon in the field, kind of standard jargon in when people talk about error correcting codes. Let me define something, which is the Hamming distance. The Hamming distance between two vectors x and y is just basically the number of entries where they differ. The distance let's say D. So the distance of the code is basically the Hamming distance between the two closest elements of the code. So this is, let's say, the min over all x not equal to y in the code of the Hamming distance between x and y. And let's say little d is the relative distance. And here I'll call, the relative distance between two code words or between two vectors is just the distance normalized by the length. So this is just D over L. Okay. So, a code is just a collection of vectors. Usually those vectors are called code words. And each one of these code words is just, you can think of a string of length L where the symbols, the alphabet, are they're basically a Q-sized alphabet. So the symbols are numbers between 1 and Q, integers between 1 and Q. And an observation suppose I take a code word from the code and arbitrarily change less than, let's say, D over 2 of its entries to obtain a corrupted version of it. And I told you I did this. So, I didn't tell you which entries I changed. And I didn't tell you what C I started with. I didn't tell you which entries I changed, and I didn't tell you what I changed them to. All you know is I took some code word, and I did this. I arbitrarily changed less than capital D over 2 of its entries to obtain a code word. Then I claim that C is uniquely determined. In other words, a third party can then come in, look at C tilde, and uniquely decode to figure out what C was. Okay. And why is that? Hamming distance is a distance, and it is a metric. So if you have all these different code words, so let's say this is C1 in the code, this is C2, and this is C3, etc. Draw balls, Hamming balls of radius D over 2 about them.
Sorry, D was the minimum distance of the code in the code word, right? In the codes, right?
That's right.
Yeah.
Yeah. So the close, there are no two code words that are less than D apart. Okay. Every pair of code words is at least D apart in Hamming distance. So this is the picture. I'll draw balls of radius D over 2 here. And I'll draw another ball here of radius D over 2. All these balls are radius D over 2. So here's a question. So now when I corrupt, and I told you I corrupted less than D over 2 of its entries, when I corrupt, I get some C tilde, which is like the corrupted version of C2. Can it be the case that, okay, so first of all, what should the decoder do? The decoder knows what the code is, so he knows what all these CIs are. So he'll just draw these balls, and he'll just return the CI such that C tilde is in its ball. Okay. When is the decoder going to run into a problem? They're going to run into a problem if C tilde is in two such balls, or more than one such ball. So can it be the case that C tilde is actually in multiple such balls? Can that happen?
No, by a triangle inequality.
By a
right?
triangle, exactly, right? By a triangle inequality. This is impossible. So you know that if it's in C4's ball, this is at most d over 2. And you also know that, again, this is at most d over 2. That implies that the distance between C2 and C4 is less than d over 2 plus d over 2 is less than d, which is a contradiction. Okay.
Should the distances from C tilde to the codes be strictly less than d over 2?
Yeah, strictly less than d over 2. So if I took a code word and I corrupted strictly less than d over 2 entries, capital D over 2 entries, then a decoder can come along and uniquely figure out what the original C was. That's the claim, right? And it's because of this picture right here. Okay, and by the way, I mean this is why they're called error correcting codes. I mean the idea is, this is a little diversion from what this course is about, but there are entire courses on error correcting codes and textbooks on error correcting codes and journals on them. Why do people care about them? And they care about them because they want to do error correction, right? So the idea is of error correction and more generally is that Alice wants to send a message. Let's call it M, which is, let's say, a qubit message. And there are many different ways Alice might want to transmit this message. The message could be a song, some digital recording of a song, and Alice wants to burn it on a CD. Or the message is going to be sent, over the internet, over a wire, through, or maybe it's over the phone, right? Alice is talking and speaking the message. And CDs can be scratched, right? Phones can have static on them. Phone lines can have static. On the internet, my connection might drop a couple packets here and there or something. And the point is, even with these kinds of, corruptions of Alice's message, I want to make sure that the person or the people at the other end can uniquely recover exactly the message that Alice sent. Okay. And that's basically what error correcting codes allow you to do. So the idea here is, Alice's message. So first of all, what I'll do, let's say, is as follows. I'll pick an injection. Let's call it ENC for encoding, which maps 0, 1. Oh, and sorry, I didn't mean to say Q because I said Q is alphabet size. So let's give me another letter, B. It maps 0 into the B into the code, meaning that each different message that Alice might want to send corresponds to a different code word. And what Alice does is Alice actually transmits not her message, but the encoding of her message, right? And as long as the channel, that's another kind of jargon word that people use in coding theory. The channel is the medium by which she transmits the message. So it's the CD or it's the phone line or whatever medium is being used. As long as the channel doesn't corrupt too many of the entries in Alice's message, like it corrupts at most d over 2 of them or less than d over 2 of them, then whoever's on the receiving end can decode and recover M exactly, right? So less than d over 2 corruptions in the channel implies can decode. more specifically, if they're, what the decoder will do is they'll be able to correct the errors and get back the actual code word that Alice sent. And then now that they have the actual code word, they can inverse the injection to get back the original b-bit string. Okay, so that's why they're called error correcting codes. For us, we're just going to more look at them as, for our lower bounds purposes, a collection of vectors that have large pairwise distances. Okay, I mean, we actually are going to think of them also as things that can be decoded or corrected. So we're going to use these now. Before I start using them to prove more lower bounds, any questions? And by the way, I should mention, this person, this by the way, I didn't write it, but I said it. This is called Hamming distance, right? And it's named after Richard Hamming, who was one of the early people in the study of error correcting codes. And there are kind of two main threads, I would say, that people study in coding theory of how to treat the whole topic of error correction. One is kind of the Hamming model, where some adversary comes and corrupts arbitrarily some fraction of your code word. Okay, that's the Hamming model. Then there's the Shannon model. So Claude Shannon is kind of the other school of error correction. And there you imagine that your channel is actually stochastic. So it's not that a worst case adversary comes and tries to choose the d/2 entries to corrupt, to screw your decoder as much as possible. No, rather there's a stochastic channel that corrupts the code word in a random way. And there are lots of different kinds of stochastic channels that people study. One common one is let's say that the code words are actually bits. So Q is 2, right? So the entries and the vectors are 0 and 1. So there's something called the binary symmetric channel, where basically for each bit independently, the channel corrupts it with some probability P, otherwise it leaves it the same. So it flips it with some probability, otherwise it leaves it the same. And then now what you want is to be able to decode with high probability, right? So anyway, just something that I thought I would mention. So the other model, if you want to read on this on your own or take a course, if you're motivated to take a course on it later, is the Shannon, basically Shannon coding. Good. So let's get back to now lower bounds. And I guess before I use these objects to prove a lower bound, there's a very natural question here, which is, do good error correcting codes exist? So I defined what it means. I defined what a code is. Do they exist? Now, kind of what does it mean now for a code to be good? When I say do good codes exist, what do I mean by that? So let's say that you fix the alphabet size. I mean, you can basically fix a bunch of the parameters and kind of let the other parameter not be fixed and ask how good you can get that parameter. So let's fix the alphabet size to Q. Let's fix the block length to L. And let's say I know that I want distance capital D. Okay. So that basically determines all the parameters here. What's the only other parameter that's left, and kind of what do you think it means for that parameter to be good? Any take
cardinality of the code, right?
Yeah, exactly, the cardinality of the code itself. So I know that the biggest it could possibly be is Q to the L. So I would love to have alphabet size Q, block length L, and min distance capital D, and have Q to the L such code words. I want this code to be as big as possible. Why? Because remember, at the end of the day, the whole way my encoding works is there's an injection from the space of messages I want to be able to send to the code, right? So you can think here basically that B is log base 2 of C, the size of C, right? I mean, let's say it has to be an integer, so let's say it's the ceiling of this. Or, no, it has to be an injection, so other way around, the floor, it can't be bigger. Okay, So yeah, the point is like, I'm sending a code word. Presumably that costs me something. It costs me to record L symbols on my CD. That's space on my CD, right? So the question I have is, for those L symbols of space that I'm wasting on my CD, how many bits B am I getting out of it? I want to get a lot of bits out of that, right? Because I'm, the more bits I'm getting out of it, the less kind of redundancy and the less space wastage in my encoding. Okay, so getting the biggest B as possible, well, B is just the logarithm of the cardinality of C. So getting B as big as possible means I'm getting the log of C as big as possible, which means I'm getting the cardinality of C as big as possible. So the name of the game is, like, if I fix these three parameters, Q, L, and D, the name of the game is get a QLD code that's as big as possible. Okay, and kind of the rate. So people talk about this in coding. There's another parameter which I'm not going to spend too much time on, but there's a parameter which is called the rate, which you can think of as like the efficiency of the encoding, right? So in this picture, basically what it's saying is, I went from, essentially I went from B bits to log base 2 of C bits, right? And the rate is defined to be that ratio. So it's basically B divided by log base 2 of C. Okay. And it's always between 1 and 0. And, I want to be as close to 1 as possible.
Wait,
Is that right? Did I goof that? No, it's in the denominator. So okay, so the point is, yeah, wait, something looks a little off here.
Wait, is
Instead of log base 2 of C, should it be?
Oh, sorry. Yeah,
the size
sorry.
of
I
where
know,
it's from?
I know what I goofed here. So what I should have said is the following. So, okay, so let's actually just say, to make my life a little simpler, let's say that I actually wanted to, the message itself is over the same alphabet. Basically, if not, you would have to introduce a log Q somewhere. So the point is, I took a B length vector and encoded it as an L length vector, right? So I blew up the length of the vector, and the ratio is the rate. Does that make sense? So if I didn't blow it up too much, then the ratio is close to 1. If I blew it up a lot, then it starts getting closer to 0. Okay. If the original alphabet was actually 0, 1, then I guess I would need to put a log Q into this ratio as well. Okay. So anyway, yeah. So the name of the game is basically I want to get as many code words as I can. So let's show that there do exist good codes, meaning that I can get the size of the code to be big. So theorem. And before I write the theorem, let me write a turn-off bound as a reminder, because we're going to use the turn-off bound to prove this. It says that, let's say, if x1 up to xn are independent, and they're each in 0, 1, and let's say x is the sum of the xi's, and let's say the expectation of x is mu, then the probability, this is the upper tail for turnoff, the probability that x is bigger than 1 plus lambda times mu, so it's bigger than its expectation by an extra 1 plus lambda multiplicative factor, is less than e to the lambda over 1 plus lambda to the 1 plus lambda to the mu. Okay. And I did include a proof of this in the lecture notes. At first I didn't, and then I thought maybe it'll be beneficial for everyone to do so. So I did update the lecture notes, and the proof is there in the probability review section. The thing to keep in mind is that, if let's imagine that lambda is actually very big, right? So it's much bigger than e. So, in the numerator I have an e to the lambda, and the denominator I have a 1 plus lambda to the 1 plus lambda. So if lambda is much, much bigger than e, then e over 1 plus lambda, the 1 plus lambda is what dominates in the denominator. And if lambda is really big, then 1 plus lambda and lambda are essentially the same, right? Then this becomes something like, just how to think about it, lambda to the minus omega lambda mu. If lambda is like much bigger than 1, let's say. So that, that's the regime that we're going to care about today. Okay. So theorem, let's say for any, given integers, let's say q and n bigger than 1, there exists a code C. Let's look right here.
What's big N?
Sorry, what? What is big N? You'll see in a second. There exists a code C, which is a subset of Q to the L for L equals big O of Q log N, such that the size of C is N, and the distance of C is at least 1 minus O of 1 over Q. I think in the notes I do the calculation a little more carefully. I think I got 1 minus 6 over Q, let's say. So good. So this is giving us something.
Distance, yeah.
Yeah, relative distance. Yeah.
Sorry, just to clarify, is the size of C like the space of all code words?
Yeah, so C is just, right? C is just a set, right? So how big is that set? How many code words do I have? Okay. Good, so let's prove this. And it's going to be a proof via the probabilistic method. And if you haven't seen such proofs, basically the idea of the probabilistic method, and there's a book called The Probabilistic Method by Alon and Spencer that has a ton of examples of this with varying levels of sophistication. But the basic idea is I'm trying to show that some object exists, right? A code exists with certain parameters. How do I show that it exists? Well, I define a distribution and I draw objects from that distribution. And I show that the probability that the object I select has that property is strictly bigger than 0, right? If it's strictly bigger than 0, that means there's some chance I get the object, which means it exists. Okay. So let me not do all the details precisely because I do have every last detail of this in the lecture notes. But the idea is to pick basically C1, Cn independently each uniformly at random from Q to the L. Okay. And then what I do is I look at the Hamming distance between, let's say, some Ci and Cj. And by the way, this collection here, I'll just define to be C. So let me just write, I don't want to, because I'm going to use indices for other things too. So let me just call them C and C prime. So here now, C and C prime, let's say, are some arbitrary different things in the code. Okay. So take two vectors in the code that have different indices. Actually, I shouldn't say it like that. So okay, sorry. Let me actually, you don't know a priori that they're different, right? Because since you chose them independently, you might get the same code word twice. So what I really should say is that CI and CJ here and I. So let's go back to the indices. Sorry about that. This is a random variable, right? And I can write it as, the sum k goes from 1 to L of like yk, where yk is an indicator random variable. Basically, it's equal to 1 if cik is equal to cjk and 0 otherwise, right? And then now I can define capital Y to be the sum over all k of yk. Oh, well, okay, I already said, so let's just call this, so let's just call this capital Y. So what do I expect capital Y to be? Well, this is just L over Q, right? Because each yk is 1 with probability 1 over Q and 0 otherwise, if these things are uniformly at random and independent. So my question is, what's the probability that Y is actually bigger than its expectation? So let's say 1 plus 5 times L over Q, right? So here, basically, this is lambda, right? I'm bigger than 1 plus lambda times my expectation. This is at most 5 to the minus omega, 5 LQ, something like that. And the point is now, look at how I chose L. Where did I choose L? So here I chose L to be basically Q times log n. That's right here. Some constant times Q log n. So the Q's cancel. I get, some, basically this is the same thing as like exp of minus omega, L over Q, right? And because I chose L to be Q log n, exp of minus omega L over Q, I can rig it so that it's much less than, let's say, 1 over n squared. Okay. So I took a fixed pair, and I said the probability that that pair is too close is, it has too much overlap, right? Having large distance is the same thing as saying I don't have much overlap in equal symbols, right? So saying that I have overlap at most 6L over Q is saying that the distance is at least L minus that. It's at least L minus 6L over Q, which means my relative distance is 1 minus 6 over Q, which is the thing that I wanted to show. So anyway, the probability that two code words are too close is at most 1 over n squared. I union bound now over all different pairs of code words. How many pairs are there? N choose 2. N choose 2 is less than n squared. So by union bound, the probability that there's some pair that's too close is strictly less than 1, which means that the probability that no pairs are too close is strictly bigger than 0, which means that there is a way, it's basically, it's possible. It's a proof of existence by the probabilistic method, right? There's some positive probability that these code words actually satisfy what I wanted, which means that the code that I want exists. Okay. Questions about that? So let's go to the next board. So let's just remember what we said here. So we said basically Q is fixed, N is fixed, and I got relative distance D, which was like something like at least 1 minus 6 over Q. And I got block length, which was O of Q log n. So corollary, given now basically, how do I want to write this? Given Q and L, and n, no, actually, I want to say this. There exists, let's call it a BQL, which is a subset of 0, 1 to the n, where n is now, let's say, q times L, such that the following are all true. 1, for all x in B, the support size of x is exactly L. What is the support size of x? Support of x is just the set of all I such that xi is not equal to 0. So it's like the one entries, basically. 2.
Sorry, what is B?
That's the corollary, is B exists. Given Q and L, there exists a B. B is a collection of n-bit vectors.
I see. Thanks.
Where n is Q times L. So all the vectors in B have the same support size. They have the same number of 1 bits, which is L. I also know that for all x not equal to y in BQL, I want to say that they don't overlap too much. So, again, bit vectors and sets are kind of the same thing, because given a bit vector, I can interpret it as a set which just contains all the ones of the bit vector. So let me abuse notation and also treat it as a set. X intersect y. So those are the bits, those are the 1 bits they have in common. That's at most 6L over Q. And 3, lastly, I want to say that this B is large. The size of B is at least exp of omega, I think I want to say L over Q. Okay.
Is this basically just interpreting the code words as as basically a matrix? Like you have.
Yeah. Yeah. Basically. I mean, so yeah, you can. Well, I mean, yeah. There's no. You can do that. There's the matrix doesn't really. You're not using any matrix operations, but Yeah.
Yeah. But basically, there's going to be a single one for each of the Q rows or something.
Yeah. So basically, you
right?
just write each symbol in unary is what you do. So,
yeah.
So right, just as you said, so you have a code word which has first of all, we know that there's a good code by the previous theorem. So that good code looks like C1, C2, CL, where each CI is a symbol between 1 and Q. And what we'll do is, for each one of these symbols, we'll just blow it up into a bit string of length Q, which has a 1 corresponding to what that thing was and a 0 everywhere else. Okay. And so now we've blown up C. C now has QL bits, because each of the L entries got blown up into a bit vector of length Q. So this is my N. And the support, the number of ones in after I do this is exactly L, right? Because each entry is giving me 1, 1. And the second item, the fact that there isn't too much overlap between distinct code words is exactly, that's basically the same thing as saying that the distance of the code was large, meaning that none of the code words overlap too much, having equal symbols. Okay. So we're going to use this corollary now to finally prove our lower bound.
Q is the alphabet size, then L is the length of the.
Yeah, so in the original code, Q is the alphabet size. Now, for B, Q is just some parameter. It's some parameter that ends up, it ends up making sure that you don't have too large of overlap between any of the bit vectors. Okay. So you can say, look, like, I want to have a large collection of bit vectors. Okay, so let's stop talking about bit vectors. Maybe it's easier if I talk about sets. Bit vectors and sets, as I said, are the same thing. I want to have a large collection of sets. Each one is a subset of 1 to n. Each set should have the same size L. Okay. I want to have a large number of sets, so that's item 3 here. The size of my collection is large. And then item 2 says none of these two sets should overlap that much, right? In principle, I could take all subsets of size L there and choose L of them. The problem is some of those differ by only one element, right? I don't want that. I want to make sure that all the sets in my collection are very different from each other. No two of them intersect that much. Okay. So that's what item 2 is giving me.
By the way, the reason that you can't make it log base 2 of Q is for the second one, right?
The reason that I cannot make...
Like we're wasting space, right? By embedding these Q alphabet words into like bit arrays of length Q. Like we could, if we wanted just to say their values, right? We could do that in log Q bits, right? But,
right. But ultimately we're taking intersection size, right? Or
yeah, but you can't do that for 2, basically, right?
For 2?
For the second part of the corollary, would not work if you did that.
That's true. It wouldn't.
Yeah,
that's true.
Okay.
So let's finally now actually prove our lower bound. Let's get out of codes and go back to lower bounds. So let's remind ourselves. I'll write in the corner of what we just said we have. So we have that BQL is a subset of 0, 1 to the n, where n is QL. Actually, let me just keep thinking of it as sets. I think that'll make our lives a little bit easier. It's a subset of like the power set of 1 to n. So it's like the power set of 1 to n is the collection of all subsets of 1 to n. I know that for all sets, let's say for all sets Q in that collection, BQL, I know that the size of Q is exactly L. I know that, what else do I know? I know that for all Q not equal to Q prime in that collection, if I look at Q intersect Q prime, that's at most 6L over Q. And I also know finally that the set is big. So the size of BQL is at least exponential in omega L over Q. Okay, so that's why I said I know. So theorem, suppose script A provides a 1.1 approximation to the number of distinct elements. More precisely, what I mean is it outputs a t tilde such that t tilde is at least t, and it's at most 1.1 times t. And is deterministic using S bits of space. Then S is omega n. So let's prove this. We will show that the existence of such an A will show that implies the existence of an injection from a big set to a small set. We'll show that there exists an injection encoding which maps basically BQL into basically 0, 1 to the S for Q is equal to 100 and L is equal to N over Q, right? Because remember, L times Q is equal to N. Okay. So how does this thing work? I should say there exists, and this thing is an injection, of course. Okay. So the encoding is as before. Meaning, we have this set that we'd like to apply the injection to. We take all elements from the set and we run our streaming algorithm over it. Okay. Then we take the memory content of the algorithm is then the encoding. So the question is the decoder. How do you do a decoder? Okay. So this is going to be a very inefficient decoder, but it will successfully decode, proving that our encoding is actually an injection. So I'll do the following. For x in, or I said now, so now it's actually sets, right? So for q in BQL, first of all, I'll do is a dot init m. So here's what I'm trying to do. I'm basically, I know that some element of BQL was encoded. I just don't know which one. So what I'm going to do is I'm going to loop over all of them, and I'm going to test, is it this one or not? Okay, and I'll show you that I can test it. So, okay, so then I'll initialize. So every time I go through the for loop, I reinitialize A to the memory contents of M. So the only thing that A has seen so far, let's say I'm here, I'm trying to recover. I want to recover, let's say, some set, I'm very bad at coming up with letters. F, such that M is just the encoding of F, right? So the question is Q equal to F or not? So every time I go through the loop, I reset the memory contents of A to be what it was right after the encoder ran A, which means that the only thing A has seen so far is F, right? So now is Q F or not? So then what I do is, for I in Q, A dot update I. So now after the for loop is over, what has A seen? Basically this is a comment now. A has seen F union Q. Right? Sorry, I did not mean to make that look like a swear word. Okay, so that was poor planning on my part. So right, so the point is, if Q were actually F, then F union Q is just F again, right? So there are two cases. Either Q was F or it isn't. If F union Q is equal to F, then what's the number of distinct elements? It's L, right? Because all the sets have exactly the same size L, which means that when we query the algorithm, it's going to output a number that's at most 1.1 L, right? Otherwise, if Q is not equal to F, then almost all the elements in Q are new because F and Q don't have a lot of overlap, which means that basically F union Q has size almost 2L, right? Which means that the output of our algorithm is going to be very large. It's going to be much larger than 1.1L. So what we say is, if a.query is at most 1.1L, then just return Q. Otherwise, we know that F union Q has size equal to the size of F plus the size of Q minus the size of the intersection. This is L. This is L. And this is at most, I said that Q was, did I pick Q? I said Q was 100. I mean, that was being very conservative. But I know that this is at most 6L over 100, which is like 0.04L. In other words, this thing here is going to be at least 1.94L. Right? So it's either going to say an answer that's less than 1.1L, or it's going to say an answer that's bigger than 1.94L. So, that's it. Questions about that?
0.06L.
0.06L?
Instead of 0.04L if it's 6 over 100.
Wait, so
On the right hand
Sorry, but
part of this
bottom
screen.
right, you said 6 over 100L equals 0.04L. Which would be 0.06L,
oh yeah,
right?
sorry. Yeah, I'm really bad at math.
This was
This
the
is-
0.94 and 0.96.
Yeah, right. Yeah. Okay. Any questions? Okay. And you could ask the question, I mean, you can tell here that kind of by the way this argument works, you'll never be able to show a lower bound. Like let's suppose that instead of 1.1, suppose that I put here, 5t, right? You'll never be able to prove a lower bound via this technique because kind of the limit of this is approximation factor of 2, right? You'll never be able to prove a lower bound for an approximation factor that's bigger than 2. Although it's known that if you are looking specifically at alpha approximation, let's say you're looking at t tilde is less than or equal to alpha t is at least t, there is an omega n over alpha bit lower bound. It's just not this argument. It's an even more sophisticated argument. And I do have a reference to it already in the notes, so you can take a look if you'd like, by Chakrabarty, and I forgot the second author's name, starts with an S, but you'll find it in the notes. Okay, good. So deterministic exact is impossible in sublinear memory. Right, and of course, so maybe I should have written it explicitly. I didn't write it explicitly, but what's the actual lower bound you get? The actual lower bound you get here, there exists this injection that implies that S has to be at least omega log, or not even just omega, but it has to be at least the logarithm of the size of BQL, which, by the guarantee that I wrote up here, is at least omega n. Okay. So let's do one more. I don't know if we're going to have a chance to do the quantiles one. I mean, it's a very similar argument. It's based on codes. It's based on this compression idea. It's just, of course, it has to be a little different because now the queries that your algorithm supports are not distinct elements queries. They're quantile queries. So you somehow have to show that being able to answer quantile queries can still let you get enough information to decode. So I probably, given that we only have 11 minutes left, I probably won't have a chance to do all the details of that. Maybe I'll just leave that as you can investigate in the notes if you're interested. But I do want to show you now the randomized distinct elements. Theorem.
I have a quick question.
Yes.
For an epsilon approximation, what is the dependence on epsilon in the lower bound?
That's a good question. So here, kind of as long as you're getting some approximation that's like strictly better than 2, you'll get a linear lower bound. And it's not, what you'd imagine is if I want 1.00001 approximation, that should be harder because I'm demanding an even better quality of approximation. Unfortunately, this particular argument is not sensitive to sending epsilon to 0. You'll still get an omega n lower bound, where the constant doesn't really depend on epsilon, or maybe the constant might converge to some fixed constant as epsilon goes to 0, but you're not going to get anything really that great. The truth is, for randomized approximate algorithms, there is a lower bound of, I'm writing this in the corner top right. There is a lower bound of omega 1 over epsilon squared log n. Okay. This lower bound is via a communication complexity argument. Remember I mentioned there are these two kind of classes of arguments, compression and communication complexity. Sorry, not times, but plus. Yeah, so 1 over epsilon squared plus log n bits is both the upper bound and the lower bound. There's a matching algorithm that achieves this. And the log n part comes from a communication problem called the equality testing, which you'll see later in the course. And 1 over epsilon squared comes from a reduction from a communication problem called gap hamming. Again, that's something that you haven't seen yet. I don't expect you to know what I'm talking about, but these are via different arguments. Those arguments don't look like what I'm showing you today. Okay,
Thanks.
No problem. So suppose now script A is a randomized exact algorithm succeeding with probability at least 2/3 using S bits of memory, then S is again omega n. Okay. Okay, so this is also, I would say, no more complicated than, or maybe even less complicated than the deterministic approximate algorithm lower bound. But it does require you to reason about things in a way that you might not have done before. So, it'll be beneficial to see this, maybe expand your mind. So the first thing is I can, A exists implies A prime exists with failure probability, let's say at most 10 to the minus 6 using O of S bits of memory. Why is that?
We can just apply the algorithm a bunch of times.
Yeah, so this is something we saw before when we talked about Morris plus and Morris plus plus and FM plus, FM plus plus. This is basically the plus plus idea, right? So A prime will just run a lot, 100 copies of A in parallel. 100 is too much. You don't even need that much, but it'll run 100 copies of A in parallel. And then at query time, it'll query all the copies. It'll get 100 different answers, and it's going to output the median. And that will work as long as at least half the copies worked, which happens with really high probability by the turnoff bound. Okay, so good. So you basically, we can get this basically for free. So from now on, I'll just assume A fails. A itself fails with probability at most 10 to minus 6. We'll show that there exists an injection, enc, which maps B into 0, 1 to the S, where B is going to be a subset of BQL, and the size of B will be at least half the size of BQL. So that implies that S is at least log the size of B, which is at least log the size of BQL over 2, which is omega n. And I'm going to again do this with Q being 100 and L being like n over Q. Again, that's conservative. That's not necessary. Okay, so how do the encoding and decoding work? Okay, so I'll call it encoding prime. That's going to be the same as the encoding from before. Why can't I just let this be my injection? Right? What is an injection? It's a function, right? Yeah, it's random. Like this is a random function. I mean, its behavior is random because it's using A, and A's behavior is random. So this is not a fixed function that's behaving in some fixed way. We'll fix that. So for right now, we have this randomized encoding. We will eventually, by the way, I mean, that's why this is a little foreshadowing. I mean, that's why I had to do this, right? That's why, why don't I just have my injection be from the entire BQL? It's because, well, yes, inc prime will end up working on the entire BQL, but I need to somehow extract the deterministic function, and I will be able to do it for a very large subset of BQL. And dec prime will be the same as for deterministic exact lower bound. So that was the one. Just I think that was here, right? So what I do is, I try to learn the bits of X one by one through this for loop. So I'm going to use the older version of the decoder And again, it's randomized because it's using A, and A is random. Okay. Now, what can I say? So the expected, remember, this is over the randomness of A, the expected number of errors from decoding by linearity of expectation, right? Each bit that I try to decode, remember now this is again, I'm viewing again, these sets F and Q as being subsets of 1 to n. So I'm trying to learn n bits here, right? So each one of these bits I'm learning, I fail with some probability 10 to the minus 6. So the expected number of errors is at most 10 to the minus 6 times n, right? Which means that the probability that, let's call it, the decoding prime of the encoding prime of some fixed set, the probability this is wrong or actually, okay, good. So let me go back here. The expected number of errors is that, which implies the probability that the number of errors is bigger than 2 times 10 to the minus 6n is less than a half. This is by Markov, right? And if I have less than 2 times 10 to the minus 6 errors, I can decode the error correcting code. That basically uniquely determines which elements of BQL I have. Okay. So I'm saying that this is true. The probability that the decoding of the encoding of F is not equal to F is less than a half. And what's the probability over? The probability is over some random string R, right? So, A, whenever you have a randomized algorithm A that's operating on some input X, this is kind of the same thing as like a deterministic algorithm operating over X comma R. So this one is deterministic. This A is random. And kind of this R here is basically like my random string. It's the source of my randomness, right? A randomized algorithm is simply a deterministic algorithm that has 2 inputs, one being the actual input and the other being the random string. Okay. So now what I can do is I can define indicator random variables. Let's define ZF is 1 if Z1 is 1 if the decoding prime of the encoding prime of F is equal to F and 0 otherwise. And what I know now is the expectation over R of the sum over all F in BQL of ZF is bigger than BQL over 2 by linearity of expectation, right? Each ZF has expectation more than a half. So the expectation of the sum is bigger than BQL over 2, which means that there exists an R, a fixed R, such that if I run inc prime d prime with, let's call this R star. It's a fixed string with R star as the random string. It's not random because it's fixed. For A, it works for at least BQL over 2 sets. And let me just call these, that's my B. So that implies that, I have an injection now from that B into 0, 1 to the S. Right? The injection is run the encoding prime algorithm with the random string being R star. And similarly, the decoding is run the decoding algorithm with the random string being R star. Okay. So questions about that?
How did you get the bound that It was greater than half on the previous page.
You're talking about this thing?
Like you used Markov's, but how did you connect that to the decoding of the encoding?
Oh, yeah. So I guess I swept that under. You mean, how did I go from here to here?
Yeah.
I guess I should say one thing, which is I do have to change one line. I do have to change one line here in the decoder. I'm not actually going to return X, but I'm going to return what I'll call like error correcting code decode of X, if that makes sense. Right. So again, it's the same kind of argument I had with these balls. So the point is I have this collection BQL of like sets of size L, and they're all pretty far apart from each other, right?
Yeah.
So if I take one of them and I corrupt it by like deleting a couple elements and adding a couple elements, I can still uniquely recover what the original set was. Right? So that's basically all I'm doing over there. I'm saying, I know that my expected number of errors introduced into F is at most n over a million by dec prime. So the probability that the number of errors is more than 2 over a million times n is less than a half. And if it's less than 2 over a million times n, that's a small enough number of errors that it uniquely identifies the element of BQL, which means that my decoding will succeed. Yeah, good question. I didn't say that explicitly.
And so does the million not depend on n?
It has to do with
like the intersection.
Yeah, like basically you don't want to get swamped, right? You know that these elements have each one of these F's has L elements in it. L is what? N over Q. Q is 100. So I have these sets that have size n over 100.
Oh, okay.
They have very small intersection with each other. Their intersection sizes are 6L over Q. So that's basically 6n over Q squared. So that's 6n over 10,000. So they have very small intersections. And then I corrupted one of them by adding 2 over a million times n extra elements in it, possibly deleting and or inserting 2n over a million elements. And I want to argue that that still basically uniquely determines what my original F was.
Yeah.
Yeah, good question. Maybe I should have said that a little slower. Any other questions? Okay. And yeah, I did not get a chance to do quantize. Let me look in the chat. I see. Okay, good.
So
yes?
the ultimate algorithm depends on this like R star.
Yeah, so R star will be kind of it's there to remove the randomness, so that I actually have like an honest to goodness function, as opposed to some randomized procedure.
Oh, okay. The decoding and encoding works on like over half of them. Well, the probability that it works is over half. So there's
right. So yeah. So for any fixed for any fixed f, I can define this random variable here. Whoops. Where's and that random variable is 1 with probability more than a half. That was what I got out of Markov. So it's 0 with probability less than a half. Right? Which means when ZF is 1, it means I succeeded in recovering F, right? So for any fixed F, this scheme works with probability more than a half. And then I use that linear rate expectation to argue that an expectation over the random choice of R, I will work. That R, an expectation works for more than half the sets. So by averaging, there must exist an R that works for more than half the sets. Not everyone can do worse than the average, right? Someone has to achieve at least the average. Okay. So good. That's all I have for you today, and I will see you all on Wednesday.